Okay, we're going to talk about the plane curves, parametric equations today, and a few things. Let's see, I'll cut that off. Okay, we call these plane curves or just curves, if you want to call it that. And what it is we have a way to take something that's in rectangular coordinates, let's say y it's f of x, or even sometimes things that are non-functions. Okay, so they don't even have to be functions. And we can write them bringing in an external parameter t, for instance, and create the same curve, same graph, or at least pieces of the graph based on the original. These are convenient when we're looking at time as a variable that the position depends on, for example. That's one application, one of the main applications. A plane curve is smooth if the derivatives f prime, g prime are continuous and not simultaneously zero, except at the endpoints. If the endpoints give us trouble, we can still work with that. It's considered piecewise smooth if you can break it into pieces on which each subinterval of that partition, and they are smooth on those subintervals for the partition, however you break up that interval I. Okay, so that becomes important in certain problems. We'll see later on. We'll have to pay attention to that. There's always ways to get around it if we need to, but we have to sometimes be careful with that when we get into the calculus portion. Okay, now, so let's take a look at how to put a graph together when you have a set of parametric equations like this. Now, notice t is not specified, so we can assume t could be anything, any real number. Occasionally, you'll see a restriction on t when the curve is presented this way, but right now we don't have it. So what we'll do is start, and we'll build a table for t, x, and y. Okay, so we're going to see what this looks like. All right, we'll start with a positive value for t, and then we'll go negative if we need to. All right, so when t is 0, we are going to have both of these at zeros from the equations. When t is, say, 1, we'll have x is a 2 and y is a 0. When t is 2, we'll have a 6 for x and a 4 minus 2 is 2 for y. When t is 3, we'll have a 9 and 3 is 12. Oops. For the x, 3 squared plus 3 is 12. 3 squared minus 3 is a 6 for that y coordinate. Okay, and we could throw in a couple negatives. Let's do -1 for t. When that happens, we get x is still 2, but y ends up as a 3. Is that right? Let's see, let's double check that. T, that'll be a 1, plus a 1 is a 2. Whoops. So let me fix that. That's 2 over there. Okay. Yeah, because 1 minus a -1. Yeah. Let's do one more. 2. -2, sorry. Let's see, we have -2, that's 4, minus 2 is 2 for the x, and 4 plus 2 is 6. Okay, so let's see if we can get these over here. Start with that. We'll start with the, I guess we'll go with the negative, which is 2, 2, 2. So that is about 1, 2, 2. Yeah, right about there. Okay. X is -1. We have a 2, 2. X is -2. We have a 2, 6. So that's over here at 2, 2, 3, 4, 5, 6. Oops. Okay. And 0 is over here. 1, 2 is right here. Oops. And 2, sorry. Whoops. You know what? Let's go backwards a little bit. I'm messing up some of these here. I was using my X's. Let's try that again. Okay. This time I use black. Okay, I'm gonna start with a 0. So I made her at the origin 0, 0. Okay, and then I'm at 2, 0, which is over here. And then I'm at 6, 2, which is here. 12, 6. Now that's way off of my grid. So I'm gonna kind of have to rough that one in. 12, it's way out here and we're up at 6. So 2, 4, 6, 9, 10, 11, 12. So it's about here and up at 2, 4, 6, right about there. So that's kind of off the charts there, but okay. Let's go back to -1, which is a 2, 2. So that is 1, 2, 2, 2 right there. And at -2, it's a 2, 6. Now something's not right with that. I think, let's try that again. Let's double check that -2 for the t. So that would be 4 minus 2 is 2. And 4 plus 2 is a 6. So that's correct. A -1 makes -1 is 1 minus 1. Ah, that's the problem. This would be a 0. Okay, sorry about that. So that point becomes 0, 2. That's actually over here. Okay, so that's my mistake. Let me get rid of that point there. That's not there. Okay. And okay, finally we got the 2, 6 here. I mean, 2, 4, 6. So there it is. There's the other one more point. Okay. 2, 4, 6. Yeah. Now you could continue. Let's say you had a -3 over here. That would make 9 minus 3 is a 6 for the x, and 9 plus 3 is be a 12. So you would be at 6 and all the way up at 12. So this would be 2, 4, 6. That's 10. So I'm going to be 2 higher over here at the 6. 1, 2. So it'll be about there. Okay, stay. Okay, and let's draw in those, connect those points with a smooth curve. Okay, so let's see. So it looks like if this is going to be a curve, I think I would have to do it like that. And this one, if it's going to be a curve, I'm thinking it's curve. It's not a line, just because even though I don't have a lot of points on here, the presence of these square terms tells me that it's nonlinear. It appears to be nonlinear, so I wouldn't just be connecting these with straight lines. Now, the order in which the points were plotted is significant. We call that the orientation. So as I moved through here, I went from 0, 0 as t increased. Okay, t was increasing. as it was, okay, as t is increasing, what's happening at these points? I started off at 0, 0, then I went to 2, 0, this point. So I'm coming this direction along the curve here. I'm sweeping this way and then continuing this way. So we would call that the orientation, and we put a little arrow on the curve like that. And that means it's actually coming in this way also, coming around this way. Okay, so the curve was actually put together that way as t increased. Our points went this way. That's called the orientation of the curve. Okay, so the orientation gives us direction in which the points were being plotted. Okay, so there's the orientation coming around that way. Okay, let's continue. The next page. Okay. Here we're going to have a little bit of practice finding a rectangular form given a parametric form. So for this one, sometimes, even though it's convenient to have these parametric forms, for purposes of graphing, it might be simpler to have the rectangular form, depending on what's in front of us. So we need to be able to go back and forth between them. Okay, and we'll have another example where we create our own equations from a rectangular equation. So we'll start with this now. What you have to do is you have to eliminate the parameter. Eliminate the parameter. So I can see that if y equals t squared and x equals t squared, a simple conclusion would be that y equals x. There it is. Parameter is gone. The only thing about this is it does not indicate all the information about the original. The original said that y was t squared, which implied that y was always positive. Same thing with x over here. X was t squared. Implied that it was, well, I shouldn't say always positive, but never negative. Same thing with x, never negative. So to keep that over here with this rectangular form, you would say that x is greater than or equal to 0 only. Okay, so you'd have to be aware of that, because if you were going to plot this curve, plot the points, turns out it's just this y equals x line. However, it's only the portion in here in the first quadrant. It's only that portion. So it would not be the portion down here. That part is gone. Okay, it's not part of this curve, this plane curve. All right, next one. Okay, sketch this curve. Now, we could go through some plotting of points, but again, and if we plot enough of them, we might see an accurate picture of the curve, but sometimes it pays to convert into rectangular form first. And we have a few of these that are, we take a standard approach. Here's what we're going to do with this. We're going to take that x minus 4 and divide it by a 2, and that's going to be equal to the cosine. And then you're going to have a y plus 1. Oops, you don't want that. Not dividing. And that's equal to the sine. Now you're trying to figure out a way to get rid of the t's in here. And you remember that if you square this, you'll have a cosine squared. And if you square this, you'll have a sine squared. And you know that if you add them, sine squared plus cosine, that's t, cosine squared of t does equal 1. That means what we have here is that, and I'm going to put them in this order, although it doesn't really matter. We have this. And you recognize that as an ellipse, right? You see that, so you get this. So now we know what we're working with. The only thing we don't know is the orientation, but we do know that this is an ellipse. We have the center 4, -1. We have the major axis parallel to x, so we have a equals 2 and b equals 1 in the y direction. So if you come over here, let's plot that center 1, 2, 3, 4, -1. It's right there. And the a is a 2, and that's in the direction of x, so it comes out this way. This way, those are the two vertices. And b is a 1, so it comes up by 1 and down by 1. And this is your curve then. Okay. And we know it's an ellipse, so we'll just kind of connect the dots there best we can. And if you want, you can also identify some of those, the other features, if you want there. So let's see, just for sake of review, yeah, those vertices are at, what do we have? We had 4 plus or minus the a, and then we had, well, I should put that in there, plus or minus the 2 with a -1. And now the foci came from that c squared equals a squared minus b squared. C was the square root of 4 minus 1 is 3, right? So foci at 4 plus or minus root 3, -1. And you had your co-vertices up here, CVs, and looks like we had a 4 with that 0. And also we had a 4 minus 2. Okay, so that's everything you need to know about it. We did more than we had to for that one. All that was asked for was the curve. Now, what about the orientation? We didn't talk about that. Because I just threw this together as a rectangular, I don't know the orientation. So to get the orientation, you'll have to check a few points. So let's let t be 0. Okay, t equals 0 implies that x will be, I'm going to go to my equation forms here. This is where I started here, but you can go backwards from here. This is convenient to look at it this way, but solving for x is going to give you 4 plus 2 cosine t, and y will be -1 plus the sine of t. Okay, so that's convenient when we're using this form. Okay. Anyway, t is 0. I get x is 6 and y is -1. So that would be this point right here. Okay, so that's right there. That's the beginning. We could say if the beginning is t equals 0, then let's pick a convenient number here. I don't want to pick this too large, but I think if I pick pi over 2, that probably, whoops, I can do pi over 4, but I'm gonna do pi over 2. Why did I write 4 if I wanted a 2? Okay, write pi over 2, and then that would imply that x from the formulas here would be a 4, and y would be 0 from your two formulas up here. So now we're over here at 4, 0. Okay, and we knew that point was there, but that shows us the direction now. It's coming around this way. Darn that thing. Okay, it's going, you see my arrows heading that way. That's the orientation. Okay. Continue now. Okay. Um, Here we have a line. It's passing through these 2 points. So first, best thing to do is, okay, let's get the rectangular form for this. I mean, we don't have enough. I mean, this is 1, 4, 5, -2. It's a line, but probably a good idea would be to look at the line in rectangular form without bringing in vectors. The notion of the vector, we don't want to talk about that yet. So anyway, let's get this line. Let's talk about the slope first. We have a 4 minus -2 over 1 minus 5, which is a 6 over -4 or -3 halves. So y minus 4 equals -3 halves x minus 1, which means that y will be -3 halves x plus 3 halves plus 4, which then becomes -3 halves x plus 11 halves. Okay, so it's basically a line. Here now you make a decision. I'm going to convert this into a parametric form. Simplest thing to do would be, let's just let x be equal to t. Then that would imply y would be equal to -3t over 2 plus 11 halves. That's good enough. That's it. That's all it takes. Something that simple. Now, there's other things you could have chosen. I noticed with my original line here, passes through these 2 points. We're assuming it passes through and continues in both directions. It doesn't say that it does not do that. So here, x is real, any real number. Over here, when you make your choice, you have to make sure that you don't violate this condition. I haven't violated it by letting x be t as long as t is real. I still have x being equal to any real number. However, if for some reason you thought that you might try a different parametric set, you might say, well, you know what, I'm going to let x be equal to t squared. Well, that would make y equal to -3 halves t squared plus 11 halves. That's okay, except that by choosing this, you now have lost the negative values for x that we had over here. We don't have them over here anymore. You can't get them because t is never negative. X is never negative here because t is squared. So you've lost it. This wouldn't give you the full curve. It would give you part of it, but you would be losing those values for which t was negative. They would not give you anything different. So this wouldn't be a good choice. Okay, here you've lost your negative values for x, which also means in here y is going to be different, isn't it? So you're not getting the same curve. You're getting a piece of it, but not the whole thing. So this would be no good. Okay, not good. It doesn't give you the whole curve. Another example might be, okay, so if that's the only problem, then just let x be t cubed. And then y would be -3 halves t cubed plus the 11 halves. This would be fine now. This would give you the same curve, and your t value, your x values could be negative depending on what t was. So this is fine. This would be a good, now it's needlessly complicated with the cubes, but it would do the same job. Same job as this one down here. Okay, they would give you the same graph. All right, so you notice you do have choices with these parametric sets. They're not unique. Okay, they are not unique. A plane curve can be represented by as many parametric forms as you can think of. So, okay, so here's another one now. Now we've been through this before, but we didn't have the equation. We had the equation in front of us. We don't have it in front of us right now. We need to create that equation first. And then we'll know what to do with it. Now there's a way to generalize this whole process, but we do need to figure out a few things first. At a minimum, finding those parameters A and B for the ellipse. We would definitely need those, and H and K. Can be systematically done, but what we'll do is this. We'll start off with, let's get a handle on what this looks like. I would start with a little sketch to make sure we have everything oriented right. So we got 4, 7, and 4, -3. So 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3. All right, so automatically we can see that this thing has a major axis coming this way, parallel to the Y. So already we can see that our, let's see, the foci, okay, so halfway across here, which is right here, is your center. Okay, and that is 4, 1, 2, 3, 4. And, you know, that's a little off. It looks like 5, 1, 2, 3, 4. I got kind of scribbly there. Let me just fix that. I'll move that over. Okay, yeah, we don't want to start off. A little more accuracy. There. It's really hard to draw these lines. Okay, so there's the C, and there's one point, and there's the other point. And that is 5 units in either direction. Remember, that's up at 7, and this is 2. 1, 2, 3, 4, 5. So you can see from here then, literally, that the A is a 5. Okay, now what we don't have is the B, but that can come from the C, which is had from these foci. 4, 5. So 4 and over at 3, 4, 5. So it's here. So that's, you can see that's the focus, and that it is 3 units. 3 units off, and I might as well put this in there. 4, 2. That's my center. So A is 5, C is 3, and now we'll be able to calculate B, because C squared is A squared minus B squared. So we get a 9 equals 25 minus B squared. That's minus 16. B is a 4. So now we have everything, and that means we can write finally x minus 2 squared over 16 plus the y minus 4. Whoops, I got that backwards, sorry. Just discovered that. Okay, let's get back in there. Okay, it's the x minus 4 and the y minus 2. Okay, and this is a 25 under here. Okay, so that's the A squared. So you see that A is larger than B, and it's the major axis is parallel to the y-axis because of that. Okay, which is consistent with the drawing. All right, now we saw how this happened before. Let's do it again. Let's just say that's a 4, we're going to let that be equal to, now you can let this be cosine or sine. What it will affect is the orientation. Because you're going to square it, it isn't going to matter. So you can say that's t, and you can have y minus 2 over 5. That would be a sine of t. So you could have flip-flopped it. It would only affect the orientation, not the equation itself. So this, notice that if we let this happen, then we will get this x minus 4. Notice it works because if you square this, 16 is cosine squared, and this y minus 2 over 5, whoops, that's 25, is the sine squared. And when you add those together, you get a 1. So this is the right way to choose your parametric form. Now, so this is my check for that. Okay, it does work. I can see that pretty quickly. Adding these would give me the 1. Anyway, if you're going to have it written like this, then I would just solve it for x. X is equal to 4 plus 4 cosine t, and y would be equal to 2 plus 5 sine t. Okay, so those are the equations. And that's all we need to do for that. Okay, now you might have said, well, what if I had switched these, this one and this one? Switch them around. Well, you would have just ended up with, you would have had that x was equal to 4 plus 4 sine t. And you would have had y was equal to 2 plus 5 cosine t. So that would have been another choice. Okay, another choice. Would have given us the same graphs, and you can show that. Now, the only thing that we don't know about these is the orientation. We're not required to show that, but back over here, you can see the graph, the 4. So we're at here, we're here, and over here. 1, 2, 3, 4 units over. And you have a graph that looks something like this. It's almost a circle, but not quite. And this point over here is at 8, 2, we can see. And this point here is obviously 0, 2. And this one up here is, we saw that already, that was our 4, 7. And this one was my 4, negative 3. Okay, so now let's look at the orientation of that. If you just pick a few values, let's say t, and we're going to look at this group first. Let's say t equals 0. That would make x equal to 8. Y equal to 2. Okay, so that's the first point here. Okay, it's beginning here. Let's pick a nice value for t. Let's say pi over 2. That makes x, again, from here, cosine of pi over 2 is 0, so we have a 4. And y would be a 7. That's the point up on top. That means we're heading along this way. There's your orientation for the first group of equations, the parametric form. This one would have a different orientation. Let's do that, and let's do a different color now. Let's try t equals 0. And we have x equals 4, y equals 7. So now, you, on the graph, you would be up here. This would be your beginning point, right at the top. So, and then let's try another one now. Let's do t equals pi over 2. That means x would be 8, and y would be 2. So this one now puts you over here, which means that's going that direction. So they've, not only do they start in different places, but they're heading in different directions. So that's, if you're going to do a simulation of motion, you'd want to keep track of that. What happens along the way? Where does a point start? Where does an object start? Where does it finish? We can also mess around with how fast it goes around this circle or this ellipse by changing the period of our functions in here. Okay, we can dictate how fast it'll traverse this entire path, the entire curve. Meaning, if t were time, then we could alter that, how fast it gets around. For the same amount of t, how fast did the point actually make a full revolution around that ellipse? We can affect the period of that progression. So that's kind of neat to play with if you can do it quickly. Calculators are nice for that. Let's see. Let's continue. Whoops, I'm in the wrong place now. Okay, we got there. Now we got this one. Okay, so this is, I guess this is the last page here. Now what we just did with those couple, we saw a little bit with the conic sections there, the ellipse and how it was handled. And this is a summary of here. If you were going to do this systematically, this form would give you a counterclockwise orientation. Major axis parallel to x-axis. Okay, major parallel to x. Notice the major has the A, okay, involved. X, okay, X and A are together. That means that's going to be your major axis, parallel to that. If you switch them around, well, in this case, this just switching sine and cosine and nothing else. All that does is change the orientation. We saw that. Now, if you want to change, this is parallel to x-axis. If you want to go parallel to y-axis, then you'll put your y with the A. It doesn't matter sine or cosine, but you'll have your equation y equals k plus a sine t, and then x with h plus b cosine t. That would be an example of getting your major in the parallel to the y. So if you associate the a, now the next thing is the hyperbola. How do you get that? Well, these are the equations that we would use for hyperbola, or this set. Okay, one or the other. Notice not only in this case, this one, what I've done here is I've changed the x and b are together, and here y and a. So the y and the a, it just depends on which one it's associated with. You gotta be careful with the parabola because you have a minus sign involved. So this one is transverse parallel to x-axis. So we've got x and the a together with the secant. This one is transverse parallel to the y-axis, and notice that we have y, a, and the secant together. Okay, so the a and the secant are going to determine which variable will be transversed with. Okay, transverse to, parallel to the secant, and that's because where this comes from. And I should show you that just briefly, because you have a tangent squared t plus 1 is the secant. So 1 equals secant squared t minus tangent squared t. So you don't have the choice of just using either variable. Whichever variable you associate the secant with, that will be your major, your transverse axis. So if I if I start with, say, x minus h, for example, x and h go together, and this would be an a, then this would give me the other one, the y minus k squared over the b squared. And you know it's equal to 1. So as long as you let the secant be equal, in other words, let the secant of t be equal to the, let's see, secant have to be h plus a, oh, that's not what I wanted. I lost my, let's see, I don't want that. I want to say this. I want to say as long as your secant of t is x minus h over a, which then makes x equal to h plus a secant t. Your x and your secant are together, so that means that will be where your a belongs. Okay, your a goes with that for positive term. Now remember, the a and the b, the size of those really doesn't dictate. It's the fact that the a goes with the positive term. So that's how you'd always have it. Anyway, let's go ahead and work this one through. So it says create the set of parametric equations, and what's the orientation? So over here now, since this is a positive term, we would want this to be the secant. So you'd say that the y minus 2 over 9 was equal to the secant of t. Okay. In fact, it's not a 9, it's a 3. Sorry about that. That's a 3. Okay, so if I let that happen, and then let the x plus 2 over 2 be equal to the tangent, then notice by squaring and subtracting, okay, you would have this result here, okay, which automatically gives you that 1, and that would give you this equation. So by squaring, subtracting the tangent squared from the secant squared, you would get the 1. You'd have your equation. So this is your form then. You would want this, solving this for y, you would have, what's that, 2 plus a 3 secant t, and here x would be negative 2 plus 2 tangent t. Okay, so this would be the right choice. So notice that secant always has to go with the positive term in the equation. And if you want to make a curve, a hyperbola where the positive, the transverse is along the y, then you have to use the secant for the y term, for the y equation. Anyway, now let's look at the orientation. It says, what's the orientation? Well, this form doesn't help us a lot, but this one does. We can do a quick graph with that without spending too much time on it. We got a is a 3, b is a 2. We're going to center at 2, negative 2. So it's here. And a is a 3, so we come up this way and down this way. And the b is a 2, so I come over this way, and I'm going to draw my rectangle in here to get ready to get my asymptotes in here. And this is very rough. I'm sure you could do a better job with your pencil and paper. And we'd be coming through this way. And down here. Now I'm going to erase those arrows just because then we'll go, okay, well, it's going to take my whole curve away. Whoa. All right, it's going crazy with that. Okay, so I don't want any arrows yet, just because I'm going to see if I can determine the orientation here. So let's pick a few points. I lost my whole X and Y plane there. Let's get those back on. That's going to be tough. This was, what was that again? X, let's see. We had X in the center was -2, 2. That's actually -2, 2. So it's actually over here. You know what? I'm gonna have to go backwards on that. I don't know how far back I can go. Oop, there it is. Okay, that's what I want. I've got that backwards. Look, you might notice this already. I got the X is -2 and the Y is 2, so it's actually over here, isn't it? So we're gonna have to let's get rid of that. Let's fix that. Yeah, let's just do this. Easier to just get that start it over again like so. Okay, so now I got my center is -2, 2. It's over here. Sorry about that. Okay, and my A is 2 units up, 1, 2, 3 units up, and 3 down. So I would put it here. And let's see. What else do we got here? Okay, so B is 2. So I'm going to come over here. Here's my rectangle. 1, 2 units here. So I'll just kind of rough that in. So, and here is what I want. Sorry about that. It's kind of a waste there. You probably notice it. You're probably saying, what are you doing? Stop. Okay, so now let's look at the orientation. Let's take a few values of t here. Let's try t equals 0. You're going to get x equals -2. And let's try t, whoops, no, y also. Y is 5, isn't it? Okay, now that's this point right here at the start, right there. That's -2, 5, so it's starting right there. Now let's try another value. Gotta be careful, this thing moves pretty quickly, so we can't pick our value too big. Let's try pi over 4. Let's see what we get. Okay, x will be equal to 0. And y will be equal to, it looks like a 5. Okay. So 0, 5, where's that? 0, 5, that doesn't make sense. Hold on. Let's see. Okay, that's my mistake. I had a 5 in here. It's 2 plus 3 root 2. because the secant of pi over 4 is root 2. It's 1 over root 2 and it's root 2. So 2 plus 3 root 2 is this number. And that's about here. Okay, right about there. Okay, so we see the orientation is coming this way. There it is. Okay, orientation this way. Now what about the bottom piece? Well, depends on how this thing swings around. Let's try another value of t. Let's try t equals, what if we had, I don't know, let's go negative pi over 4. What would happen there? Well, x would be negative 4, and y would be 2 minus, still plus 3 root 2. Okay. Yeah, negative 4. Yeah, y. Let's get that negative. Okay, so that's still positive. 2 plus 3 root 2. So let's see how that works out. Okay, so here's my number, 2 plus 3 root 2. And that is actually over here, symmetric to height to that one. So that really doesn't give us anything. It does confirm that the curve's coming in this way and swinging out that way. I guess we're going to need some different numbers. Let's try t equals, let's go with the pi over, well, see, I don't want to use the pi over 2 because it becomes infinite. The tangent becomes infinite there, and so does the secant. So we're at a point that's not even on the curve anymore. It's so far out. So this thing really kind of finishes itself off by the time we get to pi over 2. So let's take something else, like maybe pi over 3. And x would be 2 plus 3. Let's see. Cosine pi over 3. Okay, I did some computations here. I don't want to waste your time with all that. So I got t equals pi over 3. I'm trying that, and I ended up with x is 4, y is 2 plus. So on the graph, we're somewhere up in here at 1, 2, 3, 4. You know, someplace up in here. Okay. Now the next one. At t equals 3 pi over 4, we get x is negative 4 and y is 2 minus 3 root 2. Okay, so x is negative 4, it's over here, and the y is someplace down here. Okay, that's the negative, that's 2 minus 3 root 2. So it's a negative number over here someplace. Okay. Then, so now notice it's up here, but it jumped here. At pi over 2, it's kind of like the curve. I don't know if you can imagine, once hit that point, infinity, when I was heading out this way at infinity, you might imagine something like this happening. Head out to infinity and kind of got out there and came back on the other side over here. Okay, so someplace, you can imagine this whole thing kind of like spinning around almost in the third dimension, spinning around this way and eventually coming back this way. That's one way to kind of look at it. And then now it's heading this way because at pi, we get a negative 2, negative 1. That is this point over here. right here. That's -2, -1. So it is heading now this way and coming out this way. And if we go far enough, it's going to come this way because it's periodic. It's going to come this way and flip around out in infinity land. It's going to flip around and come back around this way. So it's kind of neat how you can see that happening. And last thing is I'm going to show you a little bit. So I've got the orientation, and the last thing I'm just going to pull up the calculator and play a little bit with that so you can see how you can get some of this done on the calculator. So if we'll just pause for a second. Okay, I'm going to walk through how you can get some of this on your calculator. Let's go into parametric mode. Okay, so I select my parametric mode. I'll come down. Now I'm going to stay in radians, but I'll come over to parametric mode and enter that. And go into my y equals editor, and you see these parametric forms here. And I'm going to try to get this one on here. I want I want x to be -2 plus 2 tangent. So -2 plus 2 tangent. And if I'm picking x, it automatically gives you the t. And I want y to be 2 plus 3 secant. So 2 plus 3. Now the secant is 1 over the cosine, so I got to put that in. 3 over cosine t. Okay, now we haven't paid attention to the window. I'm starting with t equals 0, and I'm going to 2 pi. So that should probably be enough to show the full graph. But what's interesting is if you slow that down a little bit, and let's say we made it only to pi, just for the fun of it. Let's make that pi instead of 2 pi. Okay, and then that's good enough. Let's see what happens here. Let's go ahead and graph that. Okay, so it went from 0. It showed part of the region that we actually graphed. Okay, it showed part of that region that we graphed. And because we went from 0 to pi. And that was, remember, we did 0 to pi and saw that region. The rest of it is apparently going to happen, or at least it can happen, if I continue out and go to 2 pi. We'll finish it. Okay, so I put in a 2 pi here, and let's see what that looks like. There's the first 0 to pi, finishes. So this is pi out to 3 pi over 2, bouncing back, coming in this way, and finishing off at 2 pi up top here. Okay, so that gives you the full, and that gave us the same orientation that we saw. Now, what happens if you change the orientation? How can you change it? Well, how do you change it without changing the equations? If you look in here, we don't want to change, we want to keep y with the secant. But what we would like to do is change, instead of that +2 here, well, we don't want to change that because that'll change the orientation. If we made this a negative secant, okay, I mean, because we're still going to square it. It isn't going to change anything if we change it to a negative, but it will change our equation. So let's do that. Let's change that to, for the y, let's change that to a negative here. Oops, that's a minus. I want a minus. Okay, and let's see what that does. Let's see if that's enough to change it. Let's go back to the graph. Okay, Actually did not change the orientation. It kind of changed the starting point. If you notice that this wasn't the same as the last one. The last one we were starting up here and went that way and came back around on this side and stopped here. But this one, actually notice what it did. Let me just go in here, just alter something and then have it regraph. This time it kind of did the second part first and then it finished. So it kind of reversed it a little bit. So, but it has the same orientation. It didn't change the orientation. All right, so let's go ahead and change something else. Let's change the other term to a positive since it was negative. Okay, and let's see how that affects it. Ah, it's still giving me the same thing. So notice the investigation. So what we changed didn't really do anything. It gave us the same exact orientation. All right, so we're going to try one more thing. Let's try just to change the sign in front of the tangent here. Let's make that a minus. I'm going to keep the other one the same. Now remember, I had changed this sign and it didn't change anything. It didn't change my orientation. I changed that -3 and left this as +2. But this time I'm going to change the 3, my tangent, make that a minus. Let's see what that does. Whoops. Okay, I want to show that change. So here we go. Graph. Now the orientation is going backwards, isn't it? So it might take a little investigation to figure out what you want to produce in terms of your orientation for your curves. But the calculator is a great tool to help you with that. And that's okay. That's about it for this one. So maybe pull that calculator out and have a little fun with this if you can.